Okay, let's try some of these for ourselves. So let's say we've got this NaOH in solution. It's dissolved in water. We call that aqueous, since it's not really specifically a solid or a liquid or a gas. It's dissolved within the liquid water, so we call it aqueous. It's going to break up into ions because this is an ionic compound. So if I were to just go with gut instinct and just roll with it, I've got an Na. Okay, I can go look that up on the periodic table, and it should make an ion with a positive 1 charge. I put a little AQ by it because it's aqueous, it's dissolved in water. Okay, I got an oxygen. Okay, I go look that up on the periodic table, and it's got a negative 2 charge. Oops. AQ for aqueous. And then I've got an H. So I go look that up on the periodic table. It should have a charge of positive 1. And it's aqueous. Okay, and this looks fine, all right? I mean, my charge all cancels out and everything, except this is totally wrong, because this isn't how the compound is built, all right? It's kind of hard to tell from looking at this if you don't have your polyatomic ions memorized, okay? But this OH is a polyatomic ion hydroxide. Okay? It's stuck together with a covalent bond. So that covalent bond between the oxygen and the hydrogen is not just going to suddenly break and turn into an ionic bond with ions separated. It's going to stick together. Okay, so my hydroxide, my OH minus, is going to stay together as OH minus. We're not going to separate it into Na plus and O and H as all 3 separate things. Okay, and if we try it like this, again, it's going to end up with the wrong Van Hoff factor. It's going to run us into messy stuff with our concentration. It's not going to work out. So I would have a polyatomic ion list handy with you if you don't have them memorized, or at least as a backup. And remember, you can't use that polyatomic ion sheet on a test, so make sure you have that in your brain before then. Okay, so let's rewrite this one. Instead of trying to split up my hydroxide into the O and the H, I want to keep hydroxide as the same polyatomic ion bonded together. So my Na plus can still break off. That is its ion, it's of its own. It's not a polyatomic or in one or something like that. Okay, but my hydroxide has got to stay together when it breaks away from that Na plus. Okay, as a general rule of thumb, anytime we start with a polyatomic ion, we're going to keep it as a polyatomic ion. We saw this a lot in chemical reactions, like single replacement and double replacement reactions. If we start with a nitrate on the left side of a reaction and we go and scramble stuff out, we usually don't end up breaking those N's and O's apart from each other. We just kind of end up with NO3 as a whole on the other side. Maybe it's bonded differently, or maybe it's been separated from its counterparts, but it still sticks together as that same polyatomic ion. The same thing goes for ion dissociation. We're going to assume that all polyatomic ions stay together the way they are. So if we look at this next one, this is magnesium hydroxide. It also has this OH minus polyatomic ion in there, and that whole thing shows up twice. I've got one here, and I've got one here. Okay, so when I go to break this up, I want to keep those hydroxides together. So I'll have an Mg2+ ion with positively 2 charged magnesium, and I'm going to have 2 of these OH minuses. Okay, so before we didn't really need to worry about balancing, but in this case, make sure that if you started with 2 of these, in parentheses, well, 2, we've got to make 2 of them on their own over here. Okay, we also do not do parentheses and then put a little 2 down there, because that implies that they are stuck together in the compound. we're not in a compound anymore. We're breaking them apart. We're dissociating them. So they should be separate from each other too. Just like the Cl minus and the Cl minus for magnesium chloride were separate. We can't take two negatively charged hydroxide ions and stick them together. So we use a number out front, a coefficient, to say they are separate ions. Okay. Now, as a general note, if you go in further in chemistry, we don't really need to write ones out in front of things that have a 1 there because it's kind of implied. I wouldn't write, Mg2 plus here if there wasn't at least one of them. Kind of for the same reason that we don't have little ones down here by this Mg or this Na and things like that. So if you go on through your kind of chemistry learning, your career, and you start to notice that these aren't showing up, that's fine. I just like to show it a lot of times so you know it is one of them. But it's not super necessary. Okay, so we've got NaOH splitting up into its separate ions. The Na plus and that OH minus polyatomic ion together. We've got our MgOH2, 2 hydroxides in there, breaking into a magnesium ion, like that guy, and 2 of our hydroxides. Drop a couple of those, it's fine, don't worry about it. Okay, we're all good, we're all good. So I'm breaking that up into 2 separate hydroxide ions. Okay. Now we're going to look at this last one here that's going to be a little bit trickier. Okay. In this case, I'm given the name. Okay. I've already got the structure figured out here, but we should figure out what that is made of, since we're going to have to write it for ourselves. Okay. It's been a while since we've taken the name of an ionic compound and turned it into a formula. So we're going to kind of step through this. So copper, Roman numeral 2, sulfate should be able to be described by a chemical formula like the stuff we've been showing up here with the letters and charges. Okay. Now, with magnesium or sodium, I could just go find it on the periodic table and see what the charge should be, but copper is in that middle section that doesn't have a shortcut in the transition metals. So that's what that Roman numeral 2 is for. What that is telling me is I'm dealing with a copper ion that has a positive 2 charge. Let's do it in a different color so it sticks out. Let's do... Okay, so our copper has a positive 2 charge in this case. Okay? If it is just something else in the periodic table in like the first couple columns or after that middle section, you can just look up and find what the charge should be. Okay. Sulfate is a polyatomic ion. So if you don't know it, you should go look it up and then memorize it. But if you do know it, you'll probably know it as SO4, and it's got a negative 2 charge. Okay, so the 2 things we're trying to put together here are a copper ion with a positive 2 charge and a sulfate ion with a negative 2 charge. Okay, we typically write charges with the number first. So Cu2 plus and SO4 2 minus. But our formula for the ionic compound together should be combining these 2 without having charges shown. So I want to make sure the charges cancel out fully. That's the sign of a good ionic compound. It's nice and stable. So if I've got something with a positive 2 charge and a negative 2 charge, positive 2, negative 2 should cancel out. That's good to go. I can just stick one of these copper ions with one of these sulfate polyatomic ions, and I make a good compound. Same goes for a positive 1 and a negative 1, or a positive 3 and a negative 3. Okay? If you don't have them match up perfectly, just write out. You just got to keep adding ions of your copper or your sulfate or whatever you're dealing with until you get your charges to cancel out. Some of them can be kind of tough, but stick with it and it will cancel eventually. If you get a subscript above 4, you might want to double check it. You might have gone too far. Okay, so I'm going to rewrite copper sulfate as its chemical formula, and I'm going to break it up into its ions. Now, the nice thing about figuring out the formula for ourselves this way is we already know what ions it's going to break up into because we just wrote them. We've got this copper 2+ ion. We've also got this sulfate polyatomic ion. The polyatomic ion is not going to break up. It's going to stay together as this. And our copper is going to stay together as copper 2+. We're just going to pull them apart from each other so they are two separately charged things. Okay, so here I've got my dissociation of copper, Roman numeral 2, sulfate, breaking up into its ions. Right, I've got my copper 2+ ion, and I've also got this sulfate ion broken apart. Okay, now the sulfate again stays together as its polyatomic ion, but my copper has separated from it. Okay, so keep your polyatomic ions together, and you should be good. If you can't find a charge on the periodic table, check your polyatomic ion list, or check to see if it's got a Roman numeral for the charge in that case.